All right, so welcome to 466 Advanced Applied Analysis. This is lecture 7, and what we're going to do today is we're going to look at convergence of series. And it turns out that the stuff we're doing in Fourier analysis, not only does it provide good approximations, but it allows us to calculate certain things that you have probably seen in the past, but might have wondered how they were computed. So we had Bessel's inequality. So let's say f is periodic, continuous, L2, some of these imply the others, then the sum of f hat of n squared, and goes from minus infinity to infinity, is less than or equal to the integral from 0 to 1 of f of x squared dx. Okay, we proved this before. I'm not going to prove the most general statement. I'll refer you to the book, which has a little bit more general than what I'm going to do. If you could change anything in this inequality, what would you change?
Information and integral.
What would it mean, though, to be integrating over n? So right now we know that this sum is less than or equal to. If you could have a change, what would you like to know? Yeah, wouldn't it be wonderful it's equal? So Bessel's equality. But actually equal.
Wait, so it's not.
It's an inequality
Okay.
that is always satisfied.
Okay.
Right? But when you look at it, it's easier to prove that it's less than or equal to. And then once you have that it's less than or equal to, then you can do a little bit more work and prove that it's equal to. Okay? So the starting point in our proof is going to be the inequality. We're going to assume f is periodic, continuous, and it's L2. This is a stronger condition than we need. How many of you have taken measure theory? Given that not one hand has been raised, I really don't want to go through the kind of argument you would use in those advanced real analysis classes. What you do is you say, I have a function that's an L2. I can find a continuous function that's very close to the function, so that the integral of my original function minus my continuous function in the L2 norm is as small as I want. So I can then say, well, rather than doing something for any generic L2 function, it's enough to do it for a continuous function. So there's a whole chain of approximations like that. This is not a measure theory class. We'll concentrate on functions that are continuous. Those are the ones that will be arising in practice. All right. So we looked at f minus Sn of f minus Sn of f. We know that this is greater than or equal to 0. And after doing some algebra, we saw, and this is where Bessel's inequality came from, minus Sn of f, Sn of f. And that led us note that the sum minus n to n of f hat of n squared was less than or equal to the integral of f of x squared dx from 0 to 1. We just brought this over to the other side. So in particular, note that this sum, we can take the limit as n goes to infinity, and it's still true. So because the sum converges, we know that the f hat ends have to be tending to 0 rapidly enough so that the sum of their squares converges. So note that this means for all epsilon, there exists an n naught such that for all n greater than or equal to n naught, the sum over n greater than or equal to n naught of f hat of n squared is less than or equal to epsilon. Because the sum converges, the tails have to converge. So if I just go down sufficiently far, I can make it as small as I want. The question then becomes, what does it mean to be sufficiently small? Okay, so where is the issue in this proof? Where's the inequality coming from? The inequality is coming from, we don't know how small this integral is, right? We know that the L2 norm of f equals this sum plus this difference. But we want to know how small is this difference. If this difference was 0, then we would have an equality. Well, if this difference was 0, then that would mean this would have to equal this, and that would mean all the Fourier coefficients would vanish from some point onward. So I do not believe we will be able to show that this is equal to 0. But maybe what we can do is we can show that as n gets very, very large, this gets very, very small. And if we can show that this goes to 0 as n goes to infinity, then we will show that this equals this in the limit, and then we'll be done. So the whole point is we want to show that this integral becomes arbitrarily small. And so we'll be doing one of my favorite things in mathematics. What will we do? I'm sorry?
Log.
Well, we need a product to do log. So, you know.
It is one of your favorite
It
things.
is one of my favorite things. But I can't do a log.
Oh.
I know. I have to do something else. Nothing is better than doing a logarithm. I agree. Or, right, so I have to do nothing. So do you think that this is a nothing by multiplying by 1 or nothing by adding 0?
I'm a little lost at where we are.
Okay, so to recap, you agree with this statement over here.
Well, is that not what we're trying to show?
No, this has the inequality.
Oh, okay.
So in other words, if I rewrite this, I get
Oh,
Yes, let's
we
read
did
that
that in last class,
this, right, the sum n goes from minus n to n of f hat of n squared plus the L2 norm of f minus Sn of f squared is equal to the integral from 0 to 1
Yeah.
of f of x squared dx. This is what we have. If we now take the limit as n goes to infinity, as n goes to infinity, this is going to go to the sum from minus infinity to infinity of f hat of n squared. And what we need is we need that to go to 0. And if we had that go to 0, then we have Bessel's equality. The challenge is we don't know right now that that goes to 0. If I assumed more about my function f, we would have it. You know, we know the Fourier series converges at a point where the function is differentiable. There's a limit to how much I'm willing to assume. You know, I'm willing to assume the function is continuous because if I give you a nice function that's L2, I can always find a continuous function that's close to it. So we just need to show that this piece goes to 0 and then we're done. So is everybody clear that all we need to do is show that the L2 norm of f minus Sn of f goes to 0? Okay, so how do we do that? So we need to add 0. So we don't know that the Dirichlet series converges to f. Oh well. Do we know anything that converges to f? The Fourier series. So we add 0. So f minus Sn of f is f minus Tn of f plus Tn of f minus Sn of f. And so now we get, I'll write it out the long way, the integral from 0 to 1 of f of x minus Sn f of x squared dx is equal to the integral from 0 to 1 of f minus Tnf of x plus Tnf of x minus Snf of x squared dx. Okay. Now, I need to show that this integral goes to 0. How might we try to show that the integral of that goes to 0? What would be a good thing to try? Okay, so
Yeah. Which is why we added 0 twice.
which is why we added 0. So this would be less than by the triangle inequality, the integral from 0 to 1 of f of x minus Tn f of x squared dx, plus the integral from 0 to 1 of Tn f of x minus Sn f of x squared dx. So much of advanced analysis comes down to dealing with absolute values. Whenever you bring an absolute value inside the integral, you make it larger. You can use the triangle inequality to say the absolute value of a sum is at most the sum of the absolute values. You lose oscillation when you do this. So in order for this to be useful, things have to be so small that you're not winning by the oscillation. Have you heard the expression close only counts in horseshoes and? Okay, I put thermonuclear warfare.
That's part 3, yeah.
That's part 3. Yep. If you're dropping in a
and bocce.
And bocce.
That's a big one.
Yep. If you're dropping a nuclear bomb, if you're off by 10 feet, does it matter? No. You just need to be roughly on target. If you have a sniper and you miss by 10 feet, very different story. You want to get a sense of how delicate is the calculation. No, but we saw this problem we tried to prove Dirichlet's theorem. We tried to put in absolute values inside, and we lost because our function was highly oscillatory. And the reason things were small was because they were oscillating, and then we had the Riemann-Lebesgue lemma. And the oscillation there gave us the term the Fourier coefficients were heading to 0. Okay, just to be clear, because I'm worried people are typing things, I'm not encouraging you to drop nuclear bombs and see how close you need to be, or just take sniper shots. I strongly protest any such behavior. But you want to get a sense when you're looking at something, how delicate is the calculation? How much leeway, how much wiggle room do I have? And so here, we expect that this is going to be really small because Tn of f is approximating f. And really, Tn of f is a weighted Dirichlet series, so this should also be small. So because I expect them to be close, I expect this to be a really good approximation. So now we have to look at each of these two pieces, and we want to show each of these pieces is small. How would we show that this piece is small? Well, by phase theorem, because f is continuous, the phase series is converging to f uniformly. So we had uniform convergence. Converges uniformly. So what that means is, for all epsilon, there exists an n naught such that if n is greater than or equal to n naught, this difference is at most epsilon. So choose n naught so large that n greater than or equal to n naught implies f of x minus Tn f of x is less than or equal to epsilon. Thus, this piece is less than or equal to epsilon. Okay? So a little bit of analysis and bookkeeping to show that we have uniform convergence, that we can show that we're getting close to all points at the same time. That handles that piece. What about this piece? Well, what we can do is we can now go through and try to figure out what exactly is this. And so Tn f of x is the sum, and goes from minus n to n, of n minus absolute value of n over n f hat of n e n of x. And Sn f of x is the sum, n goes from minus n to n, of f hat of n e n of x. To make it a little bit more easy for the comparison, I'm going to now multiply by 1. There's no need, but it's fun to multiply by 1. If only we could find a way to put a logarithm in, it would be a complete day. It makes it a little bit easier to now look at the difference. Right? When you look at them, what do we get? We get Tnf of x minus Snf of x is equal to the sum, and goes from minus n to n, of now negative absolute value of n over n f hat of n e n x. now I multiply this by its complex conjugate, and I integrate. And so, because the E ends on orthonormal basis, the only thing that survives when I multiply by the complex conjugate is the diagonal term. And I'll get the sum of n squared over n squared, f hat n absolute value squared. Are people comfortable with that, or do you want to see the algebra?
Sorry, say it one more time.
Let me show the algebra.
Yeah.
So we now have the integral from 0 to 1 of Tn f of x minus Sn f of x absolute value squared dx. This is the integral from 0 to 1 of the sum, n goes from minus n to n, of negative absolute value of n over n f hat of n e nx, and then a sum, n goes from minus n to n, of negative absolute value of n over n f hat of m complex conjugate. Complex conjugate. Because I have the norm of this squared. So I write it once and I can't use the same index. Okay? Now what happens? Well, En.
Should that be a minus n on the?
Eventually, yes, I put a complex conjugate above it.
No,
So
the minus n? Minus absolute value n, should that be n?
Oh, yes, that should be an m over here, yes. Yes. Great. So now when I look at this, I can pull out a lot of the sums. So I have a sum, n and m go from minus n to n. I will have a absolute value of n, absolute value of m over n squared, f hat n, f hat m complex conjugate, and I'll have an integral from 0 to 1 of e to the negative, so e to the 2 pi I n minus m x dx. And just using that this is e to the 2 pi I nx, this is e to the 2 pi I mx, but I take the complex conjugate, so I have a minus m. So when I do this integral, I get 0 unless n equals m. And so what I'm left with is now just the diagonal piece. N goes from minus n to n of absolute value of n squared. Well, if it's absolute value squared, I can just write it as n squared over n squared, f hat of n squared.
Sorry, can you say one more time whether we have that?
Well, because n equals m, I have absolute value of n times absolute value of n, which is just n squared.
Yeah.
So now we need to just show small. Show goes to 0 as n goes to infinity. So the first thing is, as n goes to infinity, does the sum exist? Does the sum at least converge? Is it bounded? Can you give me a sum that dominates this?
Couldn't you write f as some n? You can write it in terms of signs, right?
At this point?
The f hat n.
Well, we can write that as, it's the Fourier coefficient. We can write that as an integral. But I want to just look at this sum directly. We're trying to show that this sum is directly. Do you know any sum that's closely related to this that we know converges? So there's a sum that looks a lot like this that converges. What sum would that be? What did we start the lecture with? We started with Bessel's inequality.
Yeah.
So what can you tell me about n squared over n squared? This is less than or equal to 1.
Yeah, so you bounded by
So this thing here, it's clearly less than or equal to the sum minus infinity to infinity of f hat of n squared, which is finite. So we know at least that this sum is finite. Okay, it's not the same as showing it goes to 0, but at least it doesn't go to infinity. Now we need to do something a little bit better. we need to show that it goes to 0. So when you look at the summand, the summand is n squared over n squared f hat of n. Do you know any part of that summand that goes to infinity for certain values of little n? And if so, why does it go to 0? So do we all agree that all we have to do is show that the sum goes to 0 and the proof is done? There's been a lot of steps we've been doing. Everybody's comfortable, we've reduced it to this must go to 0 and then we win. Because if this goes to 0, then what we've now shown is
So you
this
have, like,
piece.
little epsilon left and 0 on the right.
Exactly. This piece would be small, that piece would be small, and then we've shown that this integral is small.
Yeah.
And we showed that that was enough. So all we have to do is show that that goes to 0. So what I like about this proof is you can see a lot of like a 3 epsilon proof lurking in the background. Is we're trying to break things up into different pieces and bound each piece using different techniques and then pull them together. We have a nice adding 0 by saying, well, look, I can approximate this really well using this thing. It's not what I want to look at, but it's so close to what I want to look at. Let me show that that's small, and then I'll show this other new piece is small. This is the new piece. So it's sometimes easier to do a lot of problems than to try to do the original problem fully. And so I'm going to first approximate my function f with the Fayet series. Then I'll approximate the Fayet series with the Dirichlet series. That's much better than directly comparing to the Dirichlet series. I'm finding a nice intermediate point. So we need to show the sum n goes from minus n to n of n squared over n squared f hat of n squared, or absolute value squared, goes to 0 as n goes to infinity. So we better have things going to 0 in the sum.
Yeah.
Can you tell me any part of the summand that goes to 0 and why?
1 over n squared.
I'm sorry?
1 over n squared.
We don't have a 1 over
Or n squared over n squared.
Okay.
Half n squared.
So n squared over n squared goes to 0 for little n fixed. Right? Is little n allowed to grow with n and still have this go to 0? If little n was at most n to the 1/4, oh, we haven't done any logs yet. If little n is less than equal to the log of n, all right, fine, good, we got a log n. It's not quite a natural way. Nothing on the natural log. If we have the absolute value of n is less than equal to log of n, will this still go to 0?
Yes.
Yeah.
Yes, because the n will grow exponentially with regard to little n.
Yeah. If absolute value of n is less than equal to n over log of n, will it still go to 0? Yeah. It'll be a 1 over log squared.
Yeah.
All I need is I have some bound on little n such that that bound squared over n squared tends to 0, and then those pieces will go to 0. So there's lots of different choices you can make. I think in the book I chose square root of n. Any of these will work. So we'll split up into 2 parts. Over here we'll say absolute value of n is less than equal to square root of n, and over here we'll say square root of n will be less than equal to the absolute value of n. So here we know n squared over n squared is less than equal to 1 over n. Now over here,
Yeah.
unfortunately n squared over n squared could be very large. Because we're looking at...
Okay. Yeah,
Right.
right.
Because if little n is close to big N, then that ratio is going to be damn close to 1.
Right.
So we're going to analyze it in 2 different ways. So over here, this is going to give us a sum, absolute value of n, less than equal to square root of n squared over n squared, f hat of n squared. This is less than equal to, in this range, n squared over n squared is at most 1 over n. Sum, absolute value of n, less than equal to square root of n, f hat of n squared. know about this sum?
Equal to integral from 0 to 1.
Not
Finite.
equal to, not equal to. It's finite.
We were trying to show.
It's finite.
It's finite. What's it bounded by? It's bounded by the integral from 0 to 1 of f squared.
Yeah, okay.
Right? So we know that this part here is less than or equal to 1 over n. We could make the sum go from minus infinity to infinity if we want. I could just use Bessel's inequality here. 0 to 1 of f of x squared dx. And that goes to 0. So we're using Bessel's inequality in the proof of Bessel's equality to say that this piece is small, and because little n isn't too large, we're basically saying, look, in the beginning, the Fourier series and the Fourier series are really hard to distinguish. It's only when little n gets very, very close to the boundary that you can begin to see the difference. So now let's look at this part. So here we have the sum minus n goes from absolute value of n greater than or equal to square root of n, but less than or equal to n of n squared over n squared f hat of n squared. So we're trying to show that this is small. So we want to replace this with something that's even larger that we can bound. So what would you like to do in here? How would you like to replace this? This is less than or equal to what? Square root of n, this is your n. What's something that's larger than this that we understand, that we've seen? So what are you replacing with 1? Yeah, n squared over n squared, it could be very close to 1. If you look at this interval, it's upper bounded by 1. If you look at this interval, most of the little n are going to be very close to n, right? If you have an interval going from square root of n to n, most of the mass is near n. In fact, 50% of the mass is going to be between n halves and n. 75% of the mass is going to be between n over 4 and n. It's not that big of a deal to replace this with just 1. Ah, what do we know about this? It's bounded, but it's more than just bounded. I mean, it is bounded by the whole infinite sum, but this is also bounded by the sum of absolute value of n just greater than or equal to square root of n. F hat of n. Yeah, I'll let the sum go all the way up to infinity. Why is this sum small?
Because we know the Fourier coefficients go to 0.
Okay, but the sum of 1 over n is going to 0, but that blows up. So we need a little bit more than the sum of the Fourier coefficients goes to 0. Why do we know that this sum is small? I'm sorry?
Uniform convergence?
Of what? We don't have... Why is this sum small? What do we know converges? The whole sum converges, right? If we sum from minus infinity to infinity, it converges. I'm saying now let's just sum, and let's throw away the stuff from minus root n to root n. This is the tail, right? This is the tail of a convergent sum. Because the whole sum converges, what must be true about the tail?
It's equal to 0.
Or it goes to 0. It gets small.
Yeah.
So this goes to 0 as tail of a convergent sum. Of an absolutely convergent sum. And so the full details are in the book, but we've essentially done it over here. We have Bessel's inequality tells us that the infinite sum converges. This is the tail of the infinite sum. If the tail didn't go to 0, we'd be in trouble. So that sum converges. And if we take square root of n sufficiently large, we can make this as small as we want. And now it's just a matter of putting all the pieces together. All right, choose n so that this is small, choose n so that that's small, choose n so that that's small,
Choose n as all of them.
Exactly. So take the maximum of all of them,
Yeah.
and then you win. And if you really care, you do epsilon over 3 rather than epsilon, so you can show up at the end of the day. Nobody really cares. And we actually have a 1 over n, so you can even, it's not worth making something like that. So this completes the proof, and this shows us that Bessel's inequality is actually an equality. So it's now time to ask the who gives a damn question. So we know if f is nice, then the sum from minus infinity to infinity of f hat of n squared equals the integral from 0 to 1 of f of x dx. Or, for what I want to do, I'm going to just move it from minus a half to a half. Doesn't really matter. Why would I care about having a result like this? So, if you've taken combinatorics, most of combinatorics comes down to the following. You have something you want to understand, but it's hard. And then you show it's equivalent to something that's easier to understand, which you then solve, and then you pass it backwards. What this does is this links an infinite sum with an integral. Hopefully, one of them will be doable. And if you can do one, you then get the other. So in particular, this is a way to actually evaluate sums. How many of you have seen the following fun fact? The sum of 1 over n squared, and goes from 1 to infinity, is pi squared over 6. And you can actually use this to prove that there are infinitely many primes. It's a beautiful fact. How many of you have seen a proof of this? Let's try to prove this. Okay? So let's consider f of x equals 1/2 minus the absolute value of x on the integral minus a half of x. I believe this is what I want to look at. If I cared more about you, I would have checked before the lecture. But is this function continuous?
Yes.
Yes. Is it differentiable?
No,
Not at 0. I will check and make sure that this is the function I want to look at. Yep, that's the function I want to look at. So it's not differentiable at the point x equals 0. Okay, so we've got to be a little bit careful. So Dirichlet's theorem won't be applicable. Bayes' theorem would be applicable. Let's calculate the Fourier coefficients. This function is clearly square integrable. So let's start off by calculating the integral from minus a half to a half of f of x squared dx. Do we agree that this is just twice the integral from 0 to a half? Because the function is even.
Mm-hmm.
So it's 1/2 minus x squared dx. Okay? So then the question is, what's the best way to integrate this? I would probably expand rather than risking making a mistake. It's so easy to expand. It's integral from 0 to 1/2. If we expand, we get 1/4 minus x plus x squared dx. We get 2, and when we integrate this, we get 1/4 x minus x squared over 2 plus x cubed over 3. And so we evaluate that at 0 and 1/2. So we will get 2, 1/4 times 1/2 is 1/8, minus 1/4, 1/8, plus 1/24. And so I think we get 1/12. So the integral is just 1/12. Okay, so now let's calculate the Fourier coefficients. There'll probably be a little bit more work. But we still have on the order of 10 minutes left. We should be able to do that. Also, have we calculated any Fourier coefficients yet in this course? No. So it's probably not a bad idea at some point to actually do a calculation. And then the homework problem, which you're all encouraged to do, is to actually calculate the Fourier coefficients for some of these functions and just compare how well is the Bayes series doing versus the Dirichlet series. Just because we can only prove the Bayes series is converging well does not mean the Dirichlet series is converging poorly. It just means the method of proof doesn't work for that. All right, So let's compute f hat of n is going to be the integral from minus a half to a half of f of x e to the negative 2 pi I n x dx. We've got to be a little bit careful. Let's do n equals 0 separately. So f hat of 0 is the integral from minus a half to a half of f of x dx. And this function, so here's 0, there's a half, there's minus a half. Okay. Do we need to actually go through the integration and find out what this is? Okay, can someone tell me what the integral is? 1/4. It's just 1/2 base times height. It's a triangle. Yeah. Right? So the height is 1/2, the base is 1, so it's just 1/4. I love integrating, but when there's no need, it's a little bit overkill in a graduate class to be doing an integral 1/4. All right, so we'll store that value. We know f hat of 0 equals 1/4. Now let's look at f hat of n. So now that's going to be the integral from minus a half to a half of f of x e to the minus 2 pi I n x dx. This is going to be the integral from minus a half to a half f of x cosine 2 pi n x plus I sine 2 pi n x dx. One of those two integrals is 0. Which integral is 0? The cosine integral. Why the cosine integral?
Cosine 2 pi 0. Cosine 2 pi n.
No, but n is now not 0.
Yeah, and lift small thing.
We're just doing the remaining n. Cosine is an even function, sine is an odd function. What's true about f of x? Is f of x even or odd?
Even.
It's even. The integral of
times
x,
the odd function.
even times an odd function integrates to 0. So we don't have to worry about f of x times the sine. So we just get that this is equal to the integral from minus a half to a half. And in fact, you can just go from 0 to a half and double, because it's even. So I'll go from 0 to a half, and I'll double, and I'll get 1/2 minus x times cosine 2 pi n x dx. Right. We don't have that much time left. How would you actually do this? So how would you actually do this integral? Yeah, integration by parts. I would first do the 1/2 times cosine. There'll be a sine. That's one problem. Then I have x cosine. So I'd integrate by parts that u equal x, let dv equal that. And so when the dust settles and you multiply by 2, Mathematica is telling me it's cosine n pi minus 1 over 2 n squared. Okay.
Nice result.
So now when you look at n, if n is an even number, what can you tell me about cosine n pi?
It's 1.
It's 1.
Yeah.
So if n is even, this is 0. If n is odd, then I'd get -1 minus -1, I'd get -2. And so this is equal to 0 if n is even, and it's going to equal the -2 over 2 will get -1 over, I'll write it as 2k plus 1 squared if n equals 2k plus 1. And so, unfortunately, we're not going to prove the fun fact. a little bit close. So, was there a pi in the answer? Yeah, and there's a pi squared down below, sorry. So there has to be a pi squared, and there's a pi squared excellent. Okay, so we will not prove the fun fact, we looked at the wrong one, but we'll prove something good. All right. So take the fun fact and replace that with a 4, replace that with a 4, and replace that with a 90. So now let's look at what we have. We have the sum, n goes from minus infinity to infinity, of f hat of n squared is the integral from from negative a half to a half of f of x squared dx. The n equals 0 term gave us a quarter, right? And then for everything else, we have a sum over just the odd values, right?
Yeah.
And then rather than having k be both positive and negative odd numbers, I'll just do k as a positive odd number and double. So plus twice the sum, k goes from 1 to infinity. Then we have to square the coefficient. So negative 1 squared is 1. And we'll have 2k plus 1 to the 4th over pi to the 4th equals 1/4.
Where are our negative signs?
Well, we're squaring things.
Right. Okay. Yeah.
But something is wrong here.
I think it was 112.
It was, okay, what was 112? This was the
right side.
Oh
what?
yeah.
This
One-
side?
Yeah, this was 112.
The integral of f
F of x.
squared was 112.
Yeah.
We have to we have to square this, so it's 1/16. And we have f of 0 squared. All right, so if we've done everything correctly, then we would have a sum k goes from 1 to infinity of 1 over 2k plus 1 to the 4th is going to be pi to the 4th. And then I'll have 1/12 minus 1/16. And I have to divide that by 2. So it is quite possible I've made an algebra mistake. I don't care. Yeah. The general principle is fine. You can bookkeep. And now we have a sum of the odd, the 4th powers of the odd numbers. I want a sum of just all the numbers. I don't want just the odds. But it turns out it's actually remarkably easy to pass from one to the other. So let's let S4 equal the sum n goes from 1 to infinity of 1 over n to the 4th. This is the same as the sum n goes from 1 to infinity and is even of 1 over n to the 4th plus the sum n goes from 1 to infinity of n is odd of 1 over n to the 4th. So this is the same as the sum m goes from 1 to infinity of 1 over 2m to the 4th. Right?
Yeah.
Plus a sum of k goes from 1 to infinity of 1 over 2k plus 1 to the 4th. This sum over here is 1/16. The sum m goes from 1 to infinity of 1 over m to the 4th plus the sum k goes from 1 to infinity of 1 over 2k plus 1 to the 4th. What is the sum of 1 over m to the 4th? From 1 to infinity.
S4.
It's S4. So this is just S4. So if we subtract, we get 15/16 S4 is the sum k goes from 1 to infinity of 1 over 2k plus 1 to the 4th. Or multiply both sides by 16/15. And so we'll quickly check and see if the algebra is correct. So I should have 16/15, and then I have a 1/2, and I have a 1/12 minus 1/16. And so when the dust settles, yes, it's 1/90.
Yeah.
And so we do get the sum n goes from 1 to infinity of 1 over n to the 4 is pi to the 4th over 90. So I'll make some comments on Monday's class as to how we could have gotten the 1 over n squared. We would have had to look at a different function. But hopefully this gives you some sense of the power of the results we've done. We've now found a way to actually evaluate a sum like 1 over n to the 4th exactly. And it has some really nice tricks that if you can do just the odds, you can get the evens. If you could,
Sorry. Is that a geometric interpretation of this? Like just the pi makes me think so?
I'm not sure, unfortunately, about an interpretation for this. I know the number theory interpretation, which I'll talk about on Monday. So we showed that if you know the odds, you can get the evens. If you knew the evens, could you get the odds? So I'll let you think about when we break things up. If you know the whole sum, well, I can write the whole sum basically as a nice multiple of itself. If I just knew the evens, would that have been sufficient? Or is it the odds that I needed to know? So I will leave this as things to ponder. All right, this is a good place to stop.